So we found the gravitational potential energy of an object in Earth's gravity well as this expression here. We found in general the gravitational potential energy is the mass of the two objects that are interacting divided by the distance between those two. In this case, the Earth, the mass of the Earth is interacting with the mass of the object, and the distance between the two is an Earth radius since the object is on the Earth's surface. Again, this is a negative quantity because this is a bound state. All objects on Earth's surface are bound to the Earth by the Earth's gravitational pull, and outside energy would have to be put in order to pull that object away from the Earth and allow it to escape Earth's gravity well. In order to escape the Earth's gravitational pull, we would need an input energy of equal magnitude. Basically, the gravitational potential energy is already negative. We would have to add some other energy so that our total energy would be zero, right? We have a negative quantity here because this is a bound state. If we could get the total energy back to zero, then that would mean there would be zero interaction, zero connection between us and the Earth, and we'd be free to move however we wanted to without being pulled back into orbit of the Earth or pulled back down to the Earth's surface. One form of energy that we could have would be kinetic energy. That kinetic energy, if we're going fast enough, we would be able to trade kinetic energy for gravitational potential energy, and if we had sufficient kinetic energy, it would carry us out of the Earth's gravity well and off into space. The speed with which one's kinetic energy is equal to this value of the gravitational potential energy, that is called the escape velocity. That is the velocity that you must have in order to escape the Earth's gravitational pull. If you have a velocity greater than this escape velocity, then you will lose energy as you decelerate, as the Earth pulls on you as you escape, but you'll have sufficient energy that you'll be able to pull away from the Earth's gravity and continue traveling off into space. If your velocity is less than the escape velocity, then you may make it up in the air, you may make it up into the upper atmosphere, but eventually you'll slow down and stop, and the Earth's gravity will pull you back in. You'll either fall back into orbit or fall back to the Earth. So essentially what we're saying here is that our total energy would need to be zero for us to escape, for us to no longer be bound to the Earth, and that total energy would be our kinetic energy that we'd have to have from a rocket, for example, plus the gravitational potential energy that we have with the Earth by virtue of us being on the Earth's surface. Our kinetic energy is 1/2 mv squared. Our gravitational potential energy is thus. Again, this assumes that we're on Earth and that we're on the surface of the Earth. We're starting from the surface of the Earth. Now we're going to solve for velocity. Velocity is the escape velocity, because the velocity is associated with the kinetic energy that we have to cancel out the gravitational potential energy. Since these two terms are subtracted and they equal zero, they must equal each other. And notice how I can cancel out a common term here. I can multiply both sides by 2. Cancel there. And then I'm going to square root both sides. Square root here to get rid of that, and I'm going to square root there as well. And what I end up with is that the velocity would be square root of 2 times g times mass of the Earth divided by the radius of the Earth. This is the escape velocity. This is the velocity that you'd have to achieve with your rocket in order to have sufficient energy to break away from the Earth's gravitational pull and to escape out into space. This, again, assumes that we're on Earth. We have Earth's mass here, Earth's radius, and assumes that we're starting from the surface of the Earth. But if you were on a different planet, you'd have a different mass, a different radius based on the size and density of that planet. These are both constants, and you'd have a different fixed escape velocity for a different planet that had a different gravitational pull. The fastest that anything can travel in the universe is the speed of light. We call the speed of light c, and c is equal to 3 times 10 to the 8 meters per second. That is one of the assumptions of Einstein's theory of relativity. There are, some quirks to that when you get into relativistic physics that we're going to mostly ignore for now, and we'll see in later modules. What we're interested in here is a black hole. A black hole is a super dense, supermassive lump, for lack of a better word, of mass, of material that contains as much mass as thousands or sometimes even millions of the mass of our sun in the solar system. And so you have an enormous gravitational field around that black hole. And so in order to escape the black hole's gravity, well, if you are at some arbitrary distance, RS we're going to call that, if we're at some arbitrary distance, then we would have a gravitational potential energy at that distance of capital M for the black hole and little m for our mass, and then this RS we're going to see is the distance. And so we can make the same argument that we made for the escape velocity for the Earth. To be able to escape this point at some distance from the black hole, we would need a escape velocity that would give us enough kinetic energy to be able to pull away from that black hole's gravitational potential energy. But the escape velocity can't be just any value, because the fastest anything can travel in the universe is the speed of light. So this would be our maximum possible escape velocity. Now I'll point out here that our classical equations for energy, kinetic energy, momentum, etc., all have different forms when we're talking about relativity. For here, we're going to assume the same equation for kinetic energy that we did before. This is our classical equation for kinetic energy. It's not quite the same in relativity, but again, we'll see that the details there in later modules. For right now, we'll use this as an estimate. And so if there is a limit to the velocity we can have, then there's a limit to the kinetic energy that we can have, and the limit to the kinetic energy is going to be related to a limit to how close we can get to a certain black hole of a certain mass, where we can still escape that black hole. And the distance from the black hole, what we can do is we can go ahead and calculate that. We can do the same calculation we did before. Our total energy is going to be 0, and that is our kinetic energy plus our gravitational potential energy. If we're looking for the maximum values, right, our kinetic energy here would be 1/2 mc squared, because this would be the maximum kinetic energy that would be associated with the maximum speed that we could have. And we would associate with that with the maximum gravitational potential energy we could have. That would be G times the mass of the black hole times our mass divided by RS, where this would be the minimum radius, because a smaller denominator would give us a bigger overall value, and this should be our maximum gravitational potential energy. This is the minimum radius, the minimum distance that we can be from a black hole with a given size, a given mass. We can do the same calculation that we did before. We're going to solve for what this minimum distance is, knowing that we have the speed of light here. That's a fixed value. We can cancel out the m's. We can multiply the 2 over to the side. We can divide the c squared over here, and we can multiply rs over to the other side. And we end up with rs is 2g times the mass of the black hole divided by c squared. So this is the minimum distance that we can be from a black hole of a certain height, or a certain mass, I should say, where we can still, if we go fast enough, if we reach the speed of light, we could still have enough kinetic energy to be able to break away from that black hole. Again, this isn't quite the correct equation, because this is the classical mechanical equation for kinetic energy, which we should be using the relativistic equation for kinetic energy if we're traveling near the speed of light, but this is a good estimate, and this is one of the early calculations. We call this radius here the Schwarzschild radius. And the event horizon is an imaginary circle surrounding a black hole. The laws of physics kind of break down around black holes, so kind of characterizing the interior of a black hole is pretty difficult to do because you get a lot of singularities that make the law of physics go a little bit nuts. But this circle here is the event horizon, and we often characterize a black hole by its event horizon. Everything outside the event horizon could escape if it goes sufficiently fast enough, if it has enough kinetic energy. Everything inside the event horizon is lost to us. Even if it went the speed of light, it still wouldn't have enough kinetic energy to be able to break away from the black hole's gravitational field, and so even light itself would be stuck inside that black hole.